Okay, well, welcome back today, and we're going to start regression analysis today. So last time, when we talked about scatter plots, and then we talked about correlation, and then we also talked about quantifying correlation with the correlation coefficient, and then testing whether that correlation coefficient was significant. Well, the reason why I went through that process is because it's pretty much the process that we look at when we look at data. So first of all, we look at a scatter plot to see if there's some sort of pattern and if there seems to be a relationship between two variables. And then once we see if there's a pattern or not, if there is, then we're going to go to the next step and we're going to say, okay, well, let's calculate what that correlation coefficient is using the correlation coefficient. And then once we have our correlation coefficient, if it's pretty extreme one way or the other, then we want to test whether it's significant or not. And once it's significant, then if it's a significant correlation, then we want to say, okay, what's the nature of that correlation? Meaning, what we want to do is we want to say, okay, again, we're only dealing with linear regression in this class, but we could have a nonlinear regression where we want to see what the best line or the best curve fits the data. So when we talk about regression, that's what we mean. We want to fit the best model, right? We want to fit the best model to the data. And what I mean by model, I mean mathematical modeling, where we find the best fit, either a straight line or a curve that best explains or fits the data, okay? So in this class, we're going to deal with linear regression analysis, linear regression, in the fact that we're going to try to fit the best straight line through the data. And so we're going to use the formula for a line, and that's going to be y equals mx plus b, okay? So any line, any straight line can be described using this equation, where x is the independent variable, okay, and y is the dependent variable. And so, and I talked about that before as well, that, okay, if once we want to describe the relationship between these two variables, x and y. And so the thing that describes the line is going to be the intercept and the slope, right? So m is the slope and b is the intercept. Okay, so now what we're going to do is, how do we find the best fit line? So we can do any straight line, but we want the best fit line. Okay, how do we determine the best fit line? Well, it goes back to the variation, okay? And what we want is we want the line that brings the line, we want the line that's closest to all of the values that we can possibly be. Well, how do we do that? Well, in this class, we're going to deal with what's called the least squares regression line. So there's other types of regression lines, but the most common one and the one that we're going to look at is the least squares regression line. And the least squares regression line works like this. And I'm going to just draw a picture so that help you understand what we're doing. Okay, so let's say we have a data set. I'm going to just make a really simple scatter plot. And let's say here's the line. So let's say this is the line. Okay. So we want the line, okay? And let me just illustrate something here. So let's talk about this distance here. So here's the dot. Okay? So that's the observed value, right? That's the observed value. Okay? So let's say we have let's say, let me do this. Okay, so there's the dot. So let's say this is the dot that's predicted by the regression line. Let's say this is our regression line, right? Or this is a regression line. And let's say we want, this is the dot that's based on the line, right? So what's this line? Then what does this line represent? Let's say this line represents mx plus b, right? Okay, now if it's a regression line, then the y value, we're going to put a hat on it, okay? You can either put a prime, I've seen it with a y prime, okay, or y hat, okay? So if we do y hat, then what that means is it's the predicted value. It's the value of y based on the regression line, okay? The regression equation, which we're going to talk about in a moment. But here's what we have. We have this line, and this distance, the distance from the predicted value, from the line, to the actual value, okay? So this distance, okay, that distance is what we have here in this plot. I'm going to plot this line, let me plot this ordered pair, okay? So the blue dot, the predicted value, I'm going to call that y hat, comma, oops, excuse me, not y hat, it's x comma y. Don't forget that. So x comma y hat. Okay, now, so this is all at a particular value of x, right? So at a particular value of x, I've got my predicted value based on the line and my observed value. Okay, so I've got this ordered pair. Now, this dot is the observed value, so that's going to be x comma y. That's the observed value. So this distance, this vertical distance, is the difference from what? The observed value minus the predicted value. Okay, so this distance here is what we call the residual. Okay, so this is observed value. So the observed value minus the predicted value. Okay, so in other words, it's y minus y hat. And that's what we call the residual. Okay, so now, this residual, if you take the observed value, the observed value of y is less than the predicted value. So if I do observed minus predicted, I'm going to get a negative value. But then again, if I look at this dot here, which is above the line, I'm going to get a positive residual. So I'm going to get negative residuals and positive residuals. Well, if my line is pretty much right through the middle of all of those data points, then if I add all the negative residuals and all the positive residuals, I'm going to get 0, which isn't going to help us. So what we're going to do is we're going to square all of the residuals, okay? And so what I'm going to do is I'm going to take all of those residuals, I'm going to square them, and I'm going to sum them up, and then I'm going to divide by, or excuse me, I'm just going to take that sum, and I want that sum to be the smallest value possible. This is what I'm going to do. I'm going to take all of the squared residuals. So I'm going to take all of the sum of all the squared residuals. So I'm going to take y minus y hat. Square them. Okay. And basically, I'm going to take all these squared residuals, and I want this sum to be minimized. So what I'm going to consider is the best fit line through the data is the line that makes this the smallest. Okay, and this is called, this method of regression is called least squares regression. And that's why. Because what we're going to do is we're going to take all of these different residuals, we're going to sum up, we're going to square them, sum them up, and then whichever line gives us the minimized value of this is the line we want. That's the best fit line. Okay. So now, here's the regression line for our purposes. This is the form of the least squares regression line. So it's going to be y hat or y prime, depending on the textbook. In fact, let me verify how they want this, or how they do it. Yeah, they use y hat. So good. So what we're going to do is we're going to say y hat is equal to, now here's the difference here. We're going to say b plus ax. Okay? So we, as a statistician, when it comes to regression, we always do the intercept first, followed by factors, okay, which is the x. X is what we call the factors. So we could have multiple factors in our regression line. We could go from x1 to, we could have a1, x1 plus a2, x2, and so on, okay? But we're only going to deal with one single x, okay? So here's the form. Now, we could also have this. It really doesn't matter. You can have ax plus b. It doesn't matter the order. In fact, on your calculator, you've got two options to do the regression. Option number 4, as we'll see, or option number 8. You know, we'll stick to, just got to remember what is attached to the x. Okay, is it a b or an a? Whatever's attached to the x is the slope. Okay, that's the important thing. Okay, so if we stick with this form, which is what we're mostly common with, then this is going to be our regression model. Okay, now how do we get our a and b? Well, there's a couple of formulas that we're going to show you. Now, keep in mind that these are complicated formulas. You're not going to use these formulas to calculate the slope and the y-intercept for these. Okay, just keep that in mind. So let's see here. So here are the formulas. Okay, so the formulas so again, you could do it this way, or the other one is a plus bx. Okay, so again, just watch out what's attached to the b. Okay, so whatever is attached to the x is the slope. So now, based on this, we're going to go with what they have. So it's going to be y hat equals a plus bx. Okay, so b is the slope here. Okay, so now to calculate the slope, here is the formula. It's going to be the sum of x minus x bar times y minus y bar divided by the sum of x minus x bar squared. Okay, now that's the slope. Okay, now another simpler way of doing the slope is also using this formula. You can think of it this way. It's just going to be r times the standard deviation of your x's divided by the standard deviation of your y's. So again, if you could get this from your calculator, so all three of these pieces, so you've got your x data, your y data, right, from your independent predicted values, right? So you've got your x and y data, okay? So you got your observed y's and your observed x's from your sample. Then you've got your r, which also comes from the sample, and then you could just do this. So you don't have to do this formula, but you don't even have to do that formula because I'm going to show you how to do this in the calculator very easily. Okay, in fact, we've already done it before when we're doing correlation. Okay, so now A, once you have B, then you can get A, and A is also based on a very simple formula. Actually, if you just think of y bar, take the average line. So this is the formula for the average line through the data. So y bar equals A plus b times x bar. Okay? Well, if we know b based on this formula here, which comes directly from the sample data, then we can use this formula, which is the formula for the average line through the data, the mean line. So, and then solve for a. So then a actually becomes what? A becomes y bar minus b times x bar. And so this formula and these formulas are the formula for the slope and the y-intercept. But the calculator function that will give this to you, and there's several different calculator functions that will give it to you. But the calculator functions that will give these to you is Linreg ax plus b, which is number 4. Number 8, which is Linreg a plus bx, right? So notice the difference in the form, okay? But again, they give you the same output. And the last one, which I don't know what number it is, but it's the Linreg T-Test, which is the one I like. Okay. So, and this one, now it doesn't say anything, but this one gives you the a plus bx form, okay? So again, make sure you know what you're getting from the calculator, okay? So any one of these functions will give you the regression line, okay? So just keep that in mind. This is the one I like because not only does it give you the regression line, but it gives you everything else that we use in this chapter, in chapter 12, okay? So I would stick with that one. Linreg T-Test will give you everything, okay? So now let's do an example. So now, okay, let's see here. Okay, so now here's what we have. It says, a random sample of 11 statistics students produced the following data, where X is the third exam score out of 80, and Y is the final exam score out of 200. Using the scatter plot, does it appear that we can predict the final exam score of a random student if we know the third exam score? Okay, so here's the data. Okay, I'm not going to write it on the board, but here's the data. Okay, so X is the exam score in the third exam, Y is the score on the final exam, and we want to know, is there a relationship between these two? So now I'm not going to do the scatter plot and all that, but let's just get the regression line and just see how we can figure out what the best fit line for this data is. Okay, so the first thing I'm going to do is I'm going to put it in the calculator. So I'm going to go to my stat edit, and I'm going to enter my X data, the third exam scores, into L1. So 65, 67, 71, 71, 66, 75, 67, 70, 71, 69, 69, and now L2, I'm going to enter in my Y data, which is the score on the final exam. Okay, so now I've got my two lists. Now, what I'm going to do, so here are the two lists. So that's what I have. Okay, so now what I'm going to do is I'm going to go to Stat Tests, and I'm going to go to Linreg T-Test, which is F. So I'm going to go to Linreg T-Test, and I'm going to hit Enter, and now this is what I get. Now notice at the top, there's where my L1, L2, frequency we just skip. Now now we're going to do always not equal to 0 for the row, but again, this tests for the correlation significance. Okay. Now also that Y1, the regression equation with the Y1, that's where I can go ahead and take my regression equation and store it as a function on my calculator, which I chose Y1. I'll show you that in a little bit how we do that. But the main thing is you want to make sure that L1 is in your X list, Y2, or L2 rather, is your Y list, and then if you're going to test for the significance of rho of the correlation, then you put not equals, okay, and then put Y1, as I'll show you a little later, but the main thing is getting the regression equation. So if I go down to calculate and I hit enter, this is my output. Okay, so now listen, notice at the very top it says y equals a plus bx. So that means a is my intercept, b is my slope. And what is my a? Well, right down at the bottom is a. And it says a is negative 173.513. Okay? Okay, so that's what I'm going to do. Okay, now that's a. Now if I scroll down, now there's b. Okay, so if I keep going down, in fact, if I keep hitting the down key, so right here, so if you notice, it just keeps going with more information. Okay, so notice I get my, let me go back up. Okay, so there's A and B. So A, my intercept, is negative 173.513, and my slope, B, is 4.827. So that's what I'm going to write down. So this is, so based on this example, okay, so based on this example, here's the way I would write my regression line, right? So here, I'm just going to write this on the board so you see. Okay, so A, right, so here's my line, so it's A plus BX. So A is the intercept, so A in this case is negative 173.513, and we're always going to go out to 3 decimal places for a regression. So B is 4.827. So now all I have to do is put in B and A for A and B, and I'm done. So my regression line is y hat equals what? A negative 173.513 plus 4.827 times x, and I'm done. That's my prediction line. That's my regression line. Okay, and so that's it, guys. I mean, it's that easy. Okay, and so we'll be able to go from there and ask questions regarding that. Okay, so now let's see here. What else? Let me see. Okay, so there's the regression line. Now, what if on the data set, right? So on the data set here, what do you notice? Well, what if we want to make a prediction? So what if we want to predict for a value that's inside our data set? Okay, so let's do that. Let's say, okay, well, based on the sample, here's my regression line. So this is what I'm going to use, right? So this is the best line that fits the data. Okay, now, let's say I want to predict the score on the final exam for a student who gets a 60. No, let's do who gets a 68. 68, they don't have 68 on there. We don't know 68, they don't have a value on there. But let's see, okay, well, let's say what if somebody gets a 68, okay? Well, Let's do y hat, okay? So 60, let's do 68. So now all we have to do is just plug 68 in here because x, remember, x represents the score on the third exam. So what if you got a 68? What can we predict about what the student will get on the final exam? So we'll just do this. So negative 173.513 plus 4.827 times, now this is where we're going to put in the 68. So 68, and now all I have to do is plug and chug. Okay, so now I'm going to go 4.827 times 68, and then I'm going to add that to negative 173.513. And so what's the predicted value? If a student gets a 68 on the third exam, we're going to predict that they're going to get a 154.723 on the final. Okay, that's how it works. Okay, so now, so once you have your regression line, predicting things just say are easy, right? Now, if we take a value like we just did, and we predict, and we take a value inside the range of the data, the domain, the range of the X data, the domain, right? So we take a value inside the range of the X's, okay, from our sample. Okay, so it's within the range of the X values. And we want to predict what the value is for the Y. Then we call that interpolation. Interpolation. So that is called interpolation. Now, what if we wanted to predict a value that was outside the range of our independent variable, the domain of the regression line, okay? Which means we were going to pick a number that's outside the range of our x's, okay? So for example, based on our data set, well, the minimum value in our data set is 65, and the minimum value, or the maximum value, is 71. So if we go outside that range for the x's, and let's say we use 77. Okay, let's say we want to predict the value that on the final for a student who gets a 77 on the exam. Well, this is outside the x range, the range of our x variable. Okay, the domain of the regression, or the function, if you will. So if we do that, whatever our prediction is, okay, since 77 is outside the range of the x values, that kind of prediction is called extrapolation. Okay. And so when it comes to extrapolation, our results are going to be not as good, not as reliable as if we use interpolation. Okay? Why? Because our model, our regression equation was based on that certain data set. So if we start going outside of that data set, outside of those x values, then our predictions are going to get unreliable very quickly. In fact, we don't have to go very far away from the range of the x values to have our results decrease, or the reliability of our results decrease quickly. Okay, so that's the difference between extrapolation and interpolation. Interpolation is always going to be better than extrapolation. Okay, so just keep that in mind. Okay, so now, what does this mean? Okay, we're going to talk about, so next time what we're going to do is we're going to talk about how do you interpret the slope and how do you interpret the intercept, and then we're going to do some other examples where we're going to start putting all of this together in steps for regression and correlation all together. So next time we'll start getting into the nitty-gritty of how do we interpret these things? How do we interpret the slope or the intercept based on the problem? Okay, so next time we'll discuss that. Have a good day.